Welcome everyone, and thanks for joining to our regular R&D talk. This is the series of the meetups where R&D experts and special guests and research enthusiasts share their insights on the novel technologies on the market and how they can be applied practically into the world and the business. Today, we have a very interesting session, as you can see, and that will be around the new worlds that are open to us, the 3D worlds that can be generated out of the 2D images, and the technique of efficient Gaussian splatting that may support that future. Definitely, we've seen that right now the quality of the 3D experience you have improves, maybe in Google Maps for some of the most known historical landmarks, or in generated video games environment like Genie model from Google. And this talk would uncover how those technologies are made in practice and what is the real world use cases where those can be applied. Let me introduce our today's speakers. Today with us we have Anna Stasyshin, who is R&D engineer specialized in Gaussian splatting and deep computer vision tasks. She is the Ukrainian Catholic University student, and she focuses a lot on the algorithms optimization and high performance computing. Also today with us, Oleg Basisty. He is R&D engineer that has strong mathematical background, also a student of Ukrainian Catholic University. So we have strong research group there, and he focuses on internal navigation, sensor fusion, and applying mathematical algorithms for precise state estimation and modeling. And of course, Marian Petruk. Marian Petruk is R&D lead, very experienced researcher and specialized in the generative AI, efficient LLM models deployment on the edge, as well as deep learning and computer vision. Over the past years, Marian has been leading a number of successful projects that were implemented in production in that domain. So without further ado, I want to pass the word to the speakers. But before that, just to remind you, if you have any questions during today's session, feel free to put them into the chat. So we'll have the Q&A time and speakers will be able to answer them over to you. So pass the word to Marianne.
Thank you, Bogdan. So today we would like to discuss the Gaussian splatting, and this is our research we were doing for almost a year, and we develop strong expertise and we would like to share this with the broader community. And Anna and Lech will present this topic, and I invite Anna to start. Thank you.
Someone's muted.
Oh, fine.
Today we are going to discuss Gaussian splatting. First of all, the field of computer vision is one of the key areas in artificial intelligence nowadays. And in particular, 3D vision plays a crucial role in understanding spatial information. And recently, Gaussian splatting has emerged as one of the most impactful techniques in computer vision, reshaping the entire field. So what is Gaussian splatting? It is a new technology in computer graphics and 3D representations, also regarded as novel view synthesis, which means that this technique allows having a set of images on input, generate new unseen shots of the scene or of an object. And this technique enables real-time rendering of a new scene. The Gaussian splatting was introduced in 2023 by INRIA Research Group at SIGGRAPH 2023, which is a very prestigious conference on 3D graphics. And After that, throughout last 2 years, Gaussian splatting was a very hot topic on different computer vision and graphics conferences. And also, Gaussian splatting has reached its peak popularity recently during the time of SIGGRAPH 2025 conference. So now let's take a look at how Gaussian splatting works in practice. On the screen, you can see the screenshot of a Gaussian splatting model zoomed in, and as can be seen, there are like small stretches or ellipsoids. These ellipsoids are called Gaussians, and millions of such Gaussians are used to create a smooth and photorealistic representation of a scene. Gaussians are defined by a set of parameters. First of all, it's mean mu, which basically is a position in the 3D space. Then it's a covariance matrix sigma, which represents scale and rotation of the Gaussian. And also there are colors, which are either represented with plain RGB or spherical harmonics coefficients, and opacity alpha, which is represented with a number from 0 to 1. And now, understanding what Gaussian is, let's dive into how Gaussian splatting model is created. In fact, we can split the entire model creating process into two subparts: initialization and training process. For now, let's focus on initialization, and the most common technique for initialization is a structure from motion, which is a classical computer vision algorithm which is used to estimate the camera poses, which are represented as a rotation matrix and translation vector to the first estimated camera, and a point cloud, which is a set of points in 3D and is a discrete representation of a real-world scene. And having those initialization, we can start the training process. The training process consists of 4 different parts. First of all, we render input views with the initial point cloud. And the rendering process can be as well split into several subparts. First of all, each Gaussian is projected on the image plane with the camera poses and internal camera parameters, forming an ellipse that represents the footprint. It's worth noting that the projection is non-linear, since the perspective projection distorts both covariance and mean of the Gaussian in image space. After projecting the Gaussian, we compute its contribution per each pixel. So each projected Gaussian spreads itself across nearby pixels with the 2D covariance matrix. And the contribution to each pixels is computed with the Gaussian density function, which is weighted by opacity and view-dependent colors. After that, the Gaussians are sorted by depth. They're sorted along the camera's viewing direction. Typically, it's like from the back view to the front view, handling the semi-transparent blending correctly. In fact, it ensures that farther Gaussians hide behind the ones which are close to the camera. And after that, we compute rendered image. Each Gaussian is blended with alpha composition or alpha blending, where each contributes weighted color and opacity to the pixel buffer. And this results in a very good, smooth photorealistic image where overlapping Gaussian represent the real world. After rendering the input views and projecting Gaussian, we compute loss in order to get the most accurate 3D representation. The loss used for Gaussian training is pixel-wise L2 or L1 loss, which measures color differences between the rendered image and the ground truth one. Also, a common practice for different Gaussian splatting algorithms is to include a regularization term, which adds an additional constraints to opacity, scale, or view dependent colors. After that, we propagate the gradients through our renderer to update parameters of Gaussian with gradient descent. And in fact, we can formalize the previous algorithm with this diagram. We take two images, ground truth and render, compute the loss, and then update parameters of Gaussians. After that, the density control is used. So the issue is that Gaussian splatting starts with a limited number of 3D Gaussians in a slide from structure from motion. And because of the nature of structure from motion, it can either underrepresent certain detailed regions or overrepresent flat areas. And the adaptive density control algorithm handles the issue by dynamically adjusting the Gaussian density to improve reconstruction accuracy, while keeping rendering efficient. On the screen, you can see the overrepresentation of a scene with a Gaussian. So the image is blurry and like curvy, and also you can see the underrepresentation where complex surface is rendered with too few Gaussians, resulting in a bad quality. And the adaptive density control handles it by either splitting or adding more Gaussians to fit to the rendered region. So you can see on the screen for under reconstruction, when we have two less Gaussians to represent the scene, the algorithm clones them. And when there is an over reconstruction, the algorithm tries to split it to fit the rendered feature. So we've discussed how the Gaussian splatting force works, but why does it work better than other techniques? So let's look back what was before Gaussian splatting, and we can define three basic directions. The first one is photogrammetry, which is basically a structure from motion technique we mentioned before. Another common approach is using meshes and polygons, where the scene is represented with triangles, which are obtained from the point cloud, similar to structure from motion. And the predecessor of Gaussian splatting is neural rendering with nerves, which is a method that learns continuous 3D scene from images and synthesizes new views using a neural network. On the screen, you can see different representations with these approaches. So for meshes, in fact, we take different points from the point cloud and try to fit different triangles, and Nerve obtains an explicit 3D representation by projecting rays and finding best points. And where do these traditional pipelines fail? For the photogrammetry, usually reconstruction pipelines are slow, and to obtain good enough results, they require good calibration. And also, each 3D model is in fact just a set of 3D points, so it's hard to render different lighting changes or view-dependent colors. As for the meshes, they have kind of similar problems to photogrammetry approaches. They have limited visual realism. Meshes struggle with complex lighting and transparency. And also, meshing techniques require an user intervention to model it by hand, so it may take a lot of users' time. As for the nerves, the main downsides are the training time. Usually, training nerve can take from hours to days. Also, we can't dynamically explore this scene because the frame rate FPS of scene rendered with nerve is too low. And also nerves scale poorly for large and dynamic scenes. And Gaussian splatting tackles of all of the issues mentioned before. First of all, it enables real-time rendering by directly projecting Gaussians, as we mentioned before, instead of volume sampling used in nerves. Also, it requires much less training time. It can take minutes or even seconds with new approaches instead of training for hours of days. Also, Gaussian splatting is much more scalable than nerves. It handles large and complex scenes much more efficiently due to the adaptive density control heuristics. Also, Gaussians are much more interactable than previous approaches. It supports dynamic view changes in real time. The quality itself is way better, for example, than the point cloud, and it's much easier to interpret the continuous representation than the discrete one as the point clouds. And also it bypasses mesh reconstruction and heavy neural inference for faster deployment.
So now let's talk about the applications of Gaussian splatting and where it is already making a difference and in which industries it can also create a huge impact. A quite successful example is Zillow SkyTour, which is a service they offer. It includes creating a drone capture of the property, which is later used to create a Gaussian splat of the area and the outdoors of the house, which for the users that are interested in renting or buying allows to have a clear look at the property, while for the sellers or the landlords is a great way to engage more people. So that's how it's already being used in real estate. And another way it could also be used is to create such views that are representing the indoor of the area. Another application is video games. Gaussian splatting has already been made possible to import into VR Chat, which is a platform for interactive metaverses where people can interact and with each other, and also with this like virtual scene. One thing that also is present in gaming is avatars. And while Gaussian splatting has not conquered this in practice in real video games, it is already a very hot topic on conferences, which feature a lot of research regarding creating digital twins of people using Gaussian splatting, which are editable and also represent facial movement. Film and visual effects are also something that can leverage Gaussian splatting. In fact, this year's Superman includes a Gaussian splatting, dynamic Gaussian splatting footage, which was created in collaboration with Infinite Realities. And these few shots of two people, which are like Superman's parents, is visible in the film, and it was in fact created with the Gaussian splatting methods that we have talked about. Something that unites the gaming industry and also the film industry is overall creating virtual worlds, and this can be done with several ways. For example, World Labs approached this by from a single input image, creating artificially generated additional views of the scene, which are then used to create this Gaussian splatting interactive view. And this can in fact be used for real shots, like in this example here, or as well AI-generated images. For example, this was generated with AI, and then the pipeline developed by World Labs created additional views, which were then used to create this interactive view of the same place. Or in fact, one could even use artwork, for example, paintings, which would allow people to step into the painting in 3D and look around the place that the artist was capturing. Something that is also important in our times, where a lot of notable places are at risk because of attacks, is preserving cultural heritage. And for example, this is the Gaussian splatting model of the San Francisco Sutra Tower, which was created from several shots done from a drone. The Hotel Fortress in VR chat was also made from drone footage, and as well with Gaussian splatting, and which was shown before. And this is also a way to see how it can be used to preserve cultural heritage, and to also create interactive exhibitions of such places. Outside of these existing applications, there's also future prospects for Gaussian splatting, which can make it more efficient and can make Gaussian splats be a lot easier in production than they are right now, which can further expand what areas they can be used in. For example, it's efficient Gaussian splatting, which mostly focuses on its initialization, as it often is a bottleneck for very large scenes due to the structure for motion process. And research works in several directions, from these initial implementations, such as developing a hybrid SFM methods, which do not only use the classical SFM technique, but also it incorporates global optimization and other alternatives for refinements. Also learning-based initialization, which basically use deep learning for creating the point clouds, and also the obtaining then the camera pose estimates for the Gaussian splatting input. Something that also can improve Gaussian splatting conversions is sparse to dense reconstructions. So instead of using a very sparse point cloud as an input, we further enhance the point cloud to then have less work for Gaussian splatting to do with adaptive density control, and also in working with the Gaussians, and instead have a very good starting point for the training. And also sensor fusion approaches, which may enhance the camera post estimates, which themselves affect also the quality of the point cloud, and that also speeds up the convergence of Gaussian splatting. Compaction and compression are a very important topic, and also quite popular in recent Gaussian splatting research. The reason being that the Gaussian splatting scenes take up quite a lot of storage on devices. For example, a medium-sized scene, so like a room or a very detailed a reconstruction of an object, may take up from hundreds of megabytes to gigabytes of storage. And this research also involves several directions, some of which we include here, which is compaction techniques that compromise the quality of the Gaussians and the number of Gaussians used, because that can largely it decreases the size while also maintaining a good enough quality of the renders. Also compression methods. A lot of researchers develop custom encoding algorithms and also these compressed formats in order to create a more compact way of distributing Gaussian splats. Hierarchical and clustered representations allow saving the Gaussian splatting models in a structured way, which can then be used to optimize how we render and represent these Gaussians instead of just having it stored as these sets of points. And also dynamic level of detail is a direction that is very important as well, because it would allow having a customizable size of the model, and also choose how good you wish the model to be, keeping in mind what your goals are and what are your limitations in terms of storage and also hardware for the rendering. Next step is editability and standard formats. The standard for now is .ply for Gaussian splats, and there is already a Gaussian splatting add-on for Blender for editing. But a very important thing which is not available right now is the compatibility of Gaussian splats with several other 3D model formats. That way, Gaussian splatting can be spread into a lot more applications than it is right now. And it is also available in Unreal Engine 5, which is also allowing Gaussian splatting to be used in more domains. For Gaussian splatting and dynamic scenes overall is still quite an early, it's still in its early development stages, and currently the most good quality results are shown by NVIDIA's research in this area. This would allow a lot more interaction with the scene, allowing users to not only see in real time how the scene looks when they just move around, but also move around as the motion happens in the scenes. For example, if there's an object that it's very important to capture in motion specifically. Also working with challenging scenes. Obviously, Gaussian splatting is a lot more forgiving than prior methods to these imperfections of cameras. But some things are present not only due to hardware limitations, but to what is specifically present in the scene. For example, a lot of Gaussian splatting methods struggle with some patterns, either regular or irregular, as well as places containing low features, for example, plane walls, as the initialization stage fails already at that point, as there is no key points to then create the points there. And also reflective surfaces, as the original implementation does not involve any form of ray tracing or any other technique to capture that. And research that captures that is NVIDIA's 3D GUT and GRT, which is combined into a single project. It involves, first of all, ray tracing after the regular Gaussian splatting rendering, and that allows creating scenes with reflections and not only just mirrors that have a clear reflection, but also glossy surfaces or even semi-transparent surfaces that cause light refraction that regular Gaussian splatting methods cannot capture. Also, low quality input, as mentioned before, even though Gaussian splatting gives great results even with footage from just a mobile phone, there are some things that are limiting. For example, wide field of view cameras. As before applying Gaussian splatting, these shots need to be undistorted. And as a result, the shots contain a lot more information about the scene. And once again, NVIDIA's 3D GUT handles the fisheye camera model as well, which is of great use when we want to spend less time training and also can only obtain a limited number of shots, as a wide field of view shot can contain a lot more information about the scene than a regular shot or an undistorted shot. Also, 3D data synthesis. This could be generating novel views for some computer vision tasks or augmenting data for the data sets, upscaling or downscaling images for 3D models, refining the images. And in fact, in this direction, there has been research at SoftServe where Gaussian splatting was used for upscaling the quality of 3D models. And Gaussian splatting was a crucial step in this pipeline for increasing the quality of these low resolution 3D models. Also, integration of large language models. It's also a quite broad direction for Gaussian splatting. For example, it could be to do with model concept protocol, which would incorporate developing a standard bridge between large language models and tools for working with Gaussian splatting, such as Blender or Unreal Engine or anything else that is yet to come, to have a standard of editing and refining Gaussian splatting scenes. This would allow to preserve the scene context and the history of the edits, and also allow automated and reproducible rendering tasks, and overall make scalability a lot less of an issue. And also another idea is text prompt-based editing, which would involve developing natural language control of the scene parameters, such as its density, its scale, or even lighting, colors, and so on. This would involve fast and fast editing that would be done on the level of semantics, so just text input. And another very early stage is robotics. There is quite a lot of research in this direction, which uses Gaussian splatting in different ways for edge device applications, such as using Gaussian splatting for better scene understanding and having Gaussian splatting play hand in hand with SLAM, simultaneous localization and mapping, or improve the scene interaction of these robotified agents. That's it, and we are glad to answer your questions.
Thank you so much, Anna and Oleg. Bogdan,
All right. So
the questions from the chat.
Yeah, we do have two questions. So, question from Roger Magnusson: what is the accuracy when transforming a scene from a video using this method? Can it be used for training autonomous vehicles and robots?
Yeah, it actually achieves state-of-the-art accuracy compared with other 3D representation approaches. And also the autonomous navigation with Gaussian splatting is an active research track. And as far as I know from different conference papers, people have actually utilized Gaussian splatting to implement autonomous navigation systems.
I hope Roger just answered your question. Thanks for asking that. I know that you have a good connection to those domain. Anton is asking, Anton Valigurski, is there a potential advantage of using Gaussian splatting representation for spatial understanding by autonomous system over 3D point clouds? So very similar type of question, but maybe you can elaborate a little bit more for this specific method advantage.
Yeah, and there is a potential advantage as usually different point cloud extracting approaches cannot extract all the like smaller details, and in general we can train a Gaussian splatting and obtain downsample the points and obtain like better, more dense 3D representation, and so the agent can like understand more information about the environment.
Marianne,
And also,
something good?
if I may add, so the real-time rendering is crucial for this, and also Gaussian splattings being made of Gaussians, they have opacity, they have scale, and those aspects are advantages over the point cloud. So yeah.
Okay, thanks. That makes sense, I believe, and I believe that also Dmitry want to ask the question. So Dmitry, go ahead.
Could you give us a second, please, because I did not hear the question.
Either.
Didn't-
So
but
you don't hear. Okay.
I'll let
Sure.
you know when you can like repeat, and yeah, we'll answer.
So now you can hear, right, Anna?
Yeah, now I can hear.
Okay.
Yeah.
Dmitry, if you can repeat something that you haven't said yet.
yeah, first of all, thank you for the great representation. It's interesting topic, and I would like to maybe check, and I don't know if you don't have an answer, that's also fine. So with Gaussian splatting, and there is a lot of, let's say, in 3D scene representation going on from a lot of different directions. Like we can create, generate models and so on. One of the key challenges that, for example, recreating the mesh itself using the polygons was the segmentation of the object that you want to represent. So where we are right now in terms of ability to properly make the segmentation, and if it doesn't even make sense with Gaussian splatting?
Let me maybe answer this question because I had a similar project where we actually experimented with segmentation. So basically, there are currently, this is a research topic right now, not solved yet. And you may use Gaussian splatting model inside editors like Blender or others. And there are models similar to semantic segmentation, but in 3D, where you can just select specific areas, and those areas, for example, in indoor, they will be segmented by classes like walls, tables, objects, etc. So the answer is it is possible to do. However, it is not solved yet. So it might be not that accurate, but it is doable.
I have the follow-up questions, a couple of them. So if we get to the point where we can properly make the segmentation, so how far are we from turning it into something interactable? For example, you have a box, right? And you have a scene recreated by using Gaussian splatting, and you want to move this box, for example, from one side to another one. So how far are we from that one, and what's the right now the exploration in that direction?
For this, I may say it is solved. It is already possible to do. For example, imagine we can create a Gaussian splatting of an object, for example, a table, chair, whatever. We can crop it, so we can bound from the sides, and we can use it inside the Blender, inside other editors, and move in the space. Or we can even scale it to make it smaller, larger, rotate it, even rotated to detect the angle of the surface of the area and make it properly aligned. This is also a possibility. So it is already there.
Does it intervenes like with the current solution where for rigid bodies you can use some collisions or any skeletal meshes for deformations and so on? So could it be like in the future combined or there are some challenges?
So for now, there is the field with animation of Gaussian splatting, especially with human bodies. With recently, yesterday, basically, I read the paper from that were doing Gaussian splatting of faces and even animated ones. So like to use in Zoom. Before that, it was like GANs, diffusion models, and others. But right now, Gaussian splatting seems to be able to work it as an animated objects as well. So, but it is still in progress of research. I guess it would be done soon.
Because it's really interesting. Like the other day, there was the Blender conference where they CEO of Otto, I forget Ulrich, or I forget the surname of the CEO of Otto. So he was talking about the neural rendering, and I understand that like all those different parts of 3D modeling, Gaussian splatting, neural rendering, they somehow like intersect with each other, and trying to understand like the direction where the 3D scene representation is going. Because like someday there was maybe also some of you saw there was a video where it has been instructed, for example, to move forward, right, on the horse, and it has been generated just dynamically with diffusion models. So I believe there would be combination of all these different approaches. Maybe you have, I don't know, any fresh insights in that matter, or explored anything in this direction where it can also intertwine with neural rendering and so on.
A couple of slides before, Anna actually shared the use case where like there was a usage of stable diffusions to generate more frames, and out of those, the whole scene using then Gaussian splatting was generated. So, for example, in this case, right, and before. So yes, it is possible. Where the field moves, my personal understanding is that we need to make Gaussian splatting more efficient, because right now we achieved real-time rendering, while with nerves it was not possible, and it took like huge amount of time to actually have an ability to render new views, right? Right now we achieve that, and the problem is that with current version of Gaussian splatting, we need still like an hour or even longer, depending on the quality you want to achieve, to get actually the Gaussian splatting. So the challenge right now, and we are working on this to make it more efficient, to be able to run it not only with GPUs, but even with CPUs, and in a shorter amount of time to get the model. So this is some aspects and challenges with this.
Okay, last question. I won't be annoying anymore. Does the concept of instances also can be applicable in some way in Gaussian splatting? I'll make an example. So whenever you create the 3D model, for example, of a tree, you can model 5-10 different types of leaves, and then just scatter them along all the twigs along the tree, and it would be much efficient in terms of memory. Is this something that also could be applicable in Gaussian splatting, where we would make, let's say, segmentation of the similar objects, and then just run, I don't know, the 10 different variations, and then scatter those splats around the scene, something like this?
So it is new topic for me, but what I can say, and what we did on the previous project with one of the clients, is that we generated several objects like chairs, table, and some objects on the table, and we just cloned them into specific locations. And when we were doing segmentation, we had known those objects because they were defined by us. So yes, it is a way to go. Yeah.
All right, thank you.
Thanks
Thank you.
for a lot of questions, Dimitra. Thanks for your interest, and it's happy that we have the right people on today's session who are eager to hear some more insights about that. So, if no more questions, I encourage everyone to reach out in case of any additional ones, Marianne and the team, to collaborate on that topic, because indeed, as Marianne mentioned, it evolves so rapidly and there will be intersections of different techniques to achieve better results. And for everyone who joined us today, please follow the updates and join the next R&D talk in November. Thanks, everyone, and have a good rest of the day.